Hey everybody, today we're going to be learning about conservation of momentum in two dimensions. I posted that student progress check as a Google form, so I would love for you to be able to fill that out. I've got some really great feedback on that so far, so I'll be compiling all that feedback kind of into one place, and I'll be trying to improve everything that we have going on here from home for the week returning from spring break, because we've only got one more day left after today before you guys can just chill for a week and not have to worry about doing this school from home. So I'll compile all that stuff. Some things that I'm just remembering right off the top of my head right now. A couple of you have said that you want a printable version of the formula sheet. I can totally do that for you. A few have mentioned asking for the lessons earlier in the day so that you can get them done and have nothing to do in the afternoon. Also very doable on my end. So these are great suggestions. Keep them coming in. I want to also check in on how you're all doing and how the lessons are going for you so far, what's working and what is not. So for the most part, it seems like you're all doing quite well with what we have going on. So we'll continue with that format for right now. We'll do a problem of the day now. Today is March 26th. Need to change this on my problem of the day. So let's do that. Let's present this from this slide. And now I can't see my window. There we go. Present now. Window. Boom. Okay, so here is your problem of the day. Today is technically good hair day, but because most of us are hanging out at home, I don't think we're too worried about having the best hair right now. So we got some inspiration from this gentleman right here. So good hair day. Unfortunately, my question doesn't really have anything to do with that. This is a question based off of what you were doing yesterday. So it's a problem of conservation of momentum in one dimension. When I say yesterday, I mean last lesson. So car A has a mass of 1,050 kilograms and is driving 5.1 meters per second east. Car B has a mass of 1,200 kilograms and is driving 2.9 meters per second west. If the two cars collide and lock together, so remember, we had three types of collisions that could happen. We had inelastic, we had elastic, and we had explosions. So this is an inelastic collision because they are sticking together. So if they lock together, what is going to be their velocity after the collision? So set this problem up. You're going to be looking at a momentum before equals the momentum after type scenario. Now remember, your momentum before, you will have the momentum of the one car plus the momentum of the other car. And then final, since they've stuck together, add the two masses together and you'll get the momentum of the total of the two of them stuck together after. So write it all down, give it a shot, pause the video right now and try to do it on your own. So if you paused, you should be able to come back now and I will go through the solution with you. So here is the solution. Those little boxes up above there are supposed to be arrows. Don't mind that. So the momentum before is equal to the momentum after. That means that I have mass of the first car, or the one car, we'll call it car B, times the velocity of car B initially, plus the mass of car A, plus the velocity of mass A, car A initially. Those two added together are going to be equal to the mass of the two of them together. That's 1,200 plus 1,050 times the velocity of the two when they're stuck together. So we plug in everything that we were given in the formula and we solve for VF. And if you do so, you should get something that looks like 0.83, which I have now realized that with sig figs, we want that to just be 0.8. But I wasn't thinking of that when I made this the first time. So 0.8 is your answer. And remember that you are looking at a direction. So decide on a direction to be positive, just decide on a direction to be negative. Whatever sign your final answer ends up being, that's the direction that your cars are moving. All right, let's move on to our actual notes for the day. So today we are now taking it one step further and we are discussing conservation of momentum in 2 dimensions. So this is when we have objects moving in 2 different directions instead of that are maybe going to be, perpendicular to one another or on angles rather than just having them working in the east and west or the north and south, right? The opposite directions. Now, this doesn't change the fact that during a collision, momentum is always going to be conserved, okay? So remember, the total momentum of all the objects before the collision is always going to be equal to the total momentum after the collision. Does this help? I feel like that makes it worse. Yeah, it's better. Okay, so here are the steps that we're going to use to solve momentum problems that involve angles. We are going to break all the velocity or momentum vectors into their x and y components. We're going to write an expression for the conservation of momentum in the x direction. Then we're going to write an expression for the conservation of momentum in the y direction. So this is like what we've done before in the past, splitting it up into its x and y directions. Okay, it says note, you might not always need both the x and y directions. Sometimes you only need one. This is like, think about it like a type of problem when we were looking at gravity. We only needed the y direction, not the x. Okay, or sometimes it works the other way. Then just isolate for the unknown variable, solve for that variable. That's just physics 101 right there. And if the unknown is a vector, just be sure to determine not only the magnitude, but also determine that angle and the direction in which it is moving. Okay? So those are our six steps to be able to solve these. It shouldn't change too much depending on the questions that we get. Okay? It'll be different scenarios, but for the most part, the problems that we're going to encounter, you can kind of revert back to these 6 steps to be able to solve them. Let's do an example. So a billiard ball is moving with a speed of 3 meters per second and strikes an equal mass billiard ball initially at rest. The 2 of them are observed to move off at 45 degrees. The first one, number 1, is going to be in the northeast direction, and the second one is going to be in the southeast direction. What are the speeds of the 2 billiard balls after the collision? I'm going to grab some colors here to use to solve this. That should be good. All right. So let's draw a before and after. Before and after. And in the middle here, I'm just going to say, okay, anything up, or we'll say north, is going to be positive. Anything south is going to be negative. Anything to the east will be positive, and anything to the west will be negative. Okay, that looks like a T. I don't know why I did that. There you go. Okay. So a billiard ball is moving with a speed of 3 meters per second east. So we've got one of these billiard balls. Let's make it green. We'll call it number 1. Okay. It's moving east like that. Okay. And then what it does is it strikes another billiard ball. I'm going to put it just down a little bit, and I'll explain why I'm doing that when we get to the after section. It strikes another one. We'll call it number 2, like it does in the question. Okay. So this is before. This one's traveling and this one's stationary. This one's not moving. Let's write down everything that we know before. Okay. We know that the velocity of billiard ball number 1 initially, so we'll call it V1I. And I have to add like almost a subscript on top of a subscript because I want to show that I'm talking about just the x direction. So it's V1IX. So all of a sudden we have a scenario where we have 3 subscripts going on. v1ix. All this means is that it's the velocity of billiard ball number 1 initially in the x direction. And we know that in the question it tells us that it's 3 meters per second. So I'm going to actually just put positive 3 meters per second because it's moving east. Maybe I'll add my directions here. Okay, now what about V1IY? That's the initial velocity of billiard ball number 1 in the y direction. Well, it's only moving east, therefore its y velocity initially is 0 meters per second. Okay, so that is all the information we know about the velocity of the billiard ball numbered 1 before the collision. Let's write down everything we know about billiard ball number 2. Shouldn't be that difficult. V2I in the x direction is 0 because in the question it told us that it was at rest. So that also means that V2IY is also 0 meters per second. So remember, V2IX, that means the velocity of ball. Oops, this should be green. It's color coordinated here to make it more clear. So V1, I'm just going to erase this. V2IX, that means the velocity of billiard ball number 2 initially in the x direction, and then V2IY, that means the velocity of billiard ball number 2 initially in the y direction. So there we go. Color coordinated information for us there. Now let's take a look at what happens to these two billiard balls after. It says in the question that they are observed to move off at 45 degrees, number 1 in the northeast direction and number 2 in the southeast direction. So I'm going to set up a horizontal kind of axis here for them to both have their angles measured off of. And I've got one going up 45 degrees. Okay, and that was number 1, which was our green ball. And then we have the other one going down 45 degrees. Okay, and that is our orange ball, number 2. So that's all the information we're given about after. There's one other piece of info that was just kind of hidden in here, and it's that it strikes an equal mass billiard ball. So what that means about the entire thing is that M1 is equal to M2. Okay, M1 is equal to M2. And for, just simplicity's sake, let's just call these both M. Since they're all equal, we can just call them all M. And what we'll see is since they're all equal to each other, when we end up writing out our formula, they're all going to cancel. It's going to be very nice. But first, before we do that, let's write down our final velocities. So we have got V1, that's this ball, F, that's its final velocity in the x direction, and we've got V1F in the y direction. Let's write out what these are. So V1 final in the y direction is going to be, remember, if it's in the y, that means that it's going to be the opposite, okay? Because we've got the two components. We've got the x component and we have the y component. So V1Fx, so the final velocity of ball number 1 in the x direction, is V1F cos 45. And this one is V1F sine 45. All right, because they are they're opposite and adjacent. So where does this V1F? This is just this section right here, right? This is the velocity of the total velocity on the angle of ball number 1 in the final scenario after the collision. So that is our velocities, or those are our velocities after the collision. We don't know any more information than that quite yet, but we're going to try to find them, which means that we can write out the same thing for our second ball, which is V2F in the X direction and V2F in the Y direction. Okay, well, that's a little bit harder to see over there. There we go. And what we have is a very, very, very similar scenario. We have V2F cos 45. Remember, that's just this one right here. This is V2F. And then we'll have the Y direction, V2F sine of 45. And now I realize I just did that all in orange instead of just doing an orange square around it. But you guys get the idea. As long as you can read that, that is our full scenario. I'm just going to outline this in the darker color. Okay, so now your next step is going to be to split it up into its X and Y directions and try to solve. So, what we're going to end up happening here, what we're going to end up having happen here is we're going to try to solve in either the X direction or the Y direction. And we're going to notice that we don't really have enough information for one of them on their own. So what we have here is one of those dreaded substitution scenarios that we've seen in class a couple of times. We were first introduced to them earlier in this unit when we were doing forces. Oh no, sorry, in the last unit in dynamics, we were doing forces in 2 dimensions. So we have a substitution going on. So just follow along with me here with the steps that I take, and you can go back and rewind and watch it again if you need to understand why I'm making the decisions that I'm making. But I will try to make it clear. Let's start with the Y direction. It doesn't really matter which direction we start with, but it ends up being a simpler solution for us to solve when we start with Y and plug it in the X. So what I have here is I have the momentum initially, so the momentum before in the Y direction is equal to the momentum after in the Y direction. So PIY is equal to PFY. This is just the basic principle of conservation of momentum. Now, I'm going to plug in my different values. So I have momentum is equal to mass times velocity. Now I'm just going to use m because they're all equal to each other. So rather than confusing myself, I know that all the masses are the same. So I'm just going to say m times, let's call it V1 I y. So that's the initial velocity of ball number 1 in the y direction. Okay, plus m times, let's do it for the second one, V2 IY is equal to, so that's all of my momentum in the y direction before. Now I need all of my momentum in the y direction after. So that's m times V1FY, so the final velocity in the y direction of ball number 1, plus m times V2FY, the final the final velocity in the y direction of ball number 2. Now what we see here, because all these masses are the same, is that, sorry, I don't need an arrow there, I just need to cancel these. Because that shows up in every single term, it's going to cancel. So we're not even concerned with mass. Okay, so in this case, the masses are all equal, so we can cancel them all. Now there's 2 more cancellations that come here. VIY0, or sorry, V1IY is equal to 0. So this just becomes 0. And the same goes for here. V2IY is also 0. So those are both 0. They cancel out. Now all I'm left with then is 0 on this side is equal to V1Fy. Okay, let's go over here. V1Fy is V1F sine 45. And then minus V2Fy. And V2Fy is V2F sine 45. V2F also sine 45. So this is starting to look nicer because what we can end up doing, let's move V2F, this one, let's move it to the other side. So V2F sine of 45 degrees is equal to V1F sine of 45 degrees. What can I cancel out there? I have a sine 45 in both of them, right? So the sine 45s actually cancel. So I get a really nice relationship here that V2F is equal to V1F. So what that means is that the final velocity of the two of them are actually equal. And the reason for this has to do with the fact that they're the same mass. So what ends up happening is that velocity that that first one had basically just gets split between the two of them evenly. Okay, we're not sure exactly how it gets split. It doesn't necessarily get split just straight in half. We have to solve for that. But we do know that they're going to be the same. So they're going to end up having the same velocity. It also has to do with the fact that we said that they're on the same angle. If they were on different angles, their velocity wouldn't have been split so that they're the same. So that is really nice because what we can do is just remember this for right now. And we're going to move on to the x direction and we'll be able to plug this in to actually be able to solve for a numerical value. So let's do the x direction now. I'm going to put a small divider here. Okay. Let's do the x direction. Now in the x direction, I have the same exact thing going on. I have that the momentum before in the x is equal to the momentum after in the x. So P1x is equal to PIX is equal to PFX. Now, let's do the same thing here. M times, I'm gonna, just because I'm running out of room here, my V1I is gonna be X. So V1IX is equal to 3. Okay, and then plus M, and this is of billiard ball number 2 now. So that would be, instead of V2IY, it's gonna be V2IX, which is 0. Now that is equal to M times, instead of being a V1FY, it's V1FX. So I'm going to plug in V1F cos 45. And then plus M times, instead of V2FY, we're now looking in the X. So it's V2FX, which is V2F cos 45. So M times V2F cos 45. All right. So now, again, same really nice thing. All of the M's in here are going to cancel. This entire one is going to cancel because it's 0. And what we'll end up getting then is 3 equals V1F cos 45 plus V2F cos 45. Now, pick whichever one you want, because look what happens here. Look what we have. Looking up here, I have a V1F and I have a V2F, which I also have up here. So this is going to be really nice because all I have to do, since I know that they're equal to each other, I'm just going to choose to plug one in. So I'm going to take V2F. Let's solve for V2F first. There's no reason in particular as to why. I'm just choosing one of them. I'm going to plug V2F right in there because I know that they're equal. And that's going to end up giving me a scenario where I can actually solve for a numerical value. I'm going to have 3 equals V2F cos 45 degrees plus V2F cos 45 degrees. That's just two of those, right? Those are the exact same thing. These two things are the exact same. So what this ends up becoming is 3 equals 2 times V2F cos 45 degrees. Okay, so solving for V2F, I should get V2F. I'm going to divide by 2 on both sides, divide by cos 45 on both sides, and I'll get 3 over 2 cos 45. And if I do that, if I plug that into my calculator, I know I'm starting to run out of room here. This has been a long problem. I will get 2.1 meters per second. Okay, now just a reminder, if I look back up, so now I know that V2F, and I know it's the same, right? V2F and V1F are both the same because of this, right? So if V2F I found is 2.1 meters per second, that also means that V1F is 2.1 meters per second. So we have a nice little similarity between the two of them there. That is our final answer. Now, just be careful with the questions because sometimes the questions will be worded like this. Right there. That word is very key. The question asks for the speeds, okay, not the velocities. So that means that we just need to give the magnitude of the speed. We are not required in that scenario to give the direction. Now, if we had to give the direction, it wouldn't be that bad, right? We would just have east 45 degrees north or east 45 degrees south. So we could do it very easily, but the question itself is just asking for the speeds. So don't ever do more than you need to. I feel like this has been a long enough lesson as is for today. So I'm going to save the other example for tomorrow. I'll do example number 2 for conservation of momentum in 2 dimensions. That means that we are done for the day. I look forward to reading all of your responses and tips and pointers on how things can be better for you. Hope you're doing well. You got one more day left and then you got spring break. I'll see you tomorrow.